So let's now look at order of epsilon to the first power. Right, so we can now write down the equation again for the first order problem by looking at the substitution of our expansion here. So we'll get these two terms will survive, and we'll now pull out a right hand side of -1 from this equation. Equals -1. Now we can solve the problem the similar way we did before, except we now have a non-homogeneous right hand side. So we would then need a particular solution for this. So again, if we write the resultant equation is so the homogeneous solution is the same as before, but I now need a particular solution, which in this case you'll see is just -1. So I should be able to get basically y equals -1 plus now b1 as the new constant at the first order, e to the minus x tilde. So this just means that dg by dx is equal to this. So after I do one integration, I can write out that g1 is simply, so if I just integrate this once over to get g1, so I get minus x tilde minus b1 e to the minus x tilde plus a constant c1. And if I apply the boundary condition, I will find, again, because this will go to 0, this term goes to 1, that c1 is equal to b1. And so I get my new solution at the first order to be simply minus x tilde plus b1 into 1 minus e to the minus x tilde. Right, so now having obtained this, I can write my basically solution, the x inner solution, of course near x equal to 0, right, as b naught into 1 minus e to the minus x tilde plus epsilon times minus x tilde plus b1 1 minus e to the minus x tilde. And then I have my outer solution, right, which was just my outer solution which we obtained right at the beginning is just the following: e to the minus x plus a constant Alright, so now I have the two solutions, but I have an unknown constant a naught and a1 which have to be determined by one of the boundaries. If x equal to 0 is indeed, if there is indeed a boundary layer in x equal to 0, then this a naught and a1 would get ultimately determined from the boundary at x equal to 1. So for our current purpose, let's assume that a naught and a1 will ultimately be known separately. And proceeding under that assumption, the only unknowns here are b naught and b1. And the objective now is to find those unknowns by matching the inner solution near x equal to 0 to the outer solution which is far from the boundary x equal to 0. So this now brings us to the key of this lecture, which is asymptotic matching. So there are a couple of ways of doing this. One is to actually introduce another variable, let's say x double tilde, which is stretched by epsilon to the alpha, where alpha is somewhere between 0 and 1. So that means it's an intermediate variable. If alpha is 0, then the variable is just x. If alpha is 1, then the variable is x tilde. But if alpha is between 0 and 1, it's an intermediately stretched variable. If we substitute that, if we make that substitution in both these inner and outer solutions so that we get them in terms of a single variable, let's say x double tilde, and then we try to compare their forms, and from that figure out what b0 and b1 should be. This is a somewhat tedious procedure, although it's more systematic. There is a sort of shorter way of doing this, which almost always works, and which is what we will look at today, which is Van Dijk's matching rule. Alright, and his rule basically says that you take the outer limit. So you apply the outer limit on the inner solution, and what you obtain from there should be equal to the inner limit of the outer solution. So what this basically says is, if I look at the inner solution and I look at how it behaves far away from the boundary, that should be equal to what I get if I look at the outer solution as I approach the boundary x equal to 0. So how do we do this mathematically? So what we need to do is we need to go to f inner, which we remember is a function of x tilde, but I will replace x tilde in x inner by x by epsilon, and then take the limit of epsilon going to 0. So you see what this does is, if epsilon goes to 0 for a fixed value of x, remember x tilde goes to infinity. So it's like taking x tilde to large values, but making the substitution and then taking epsilon to 0 is a more systematic way of doing it, and which respects the true meaning of the limit, the outer limit of the inner solution. And then we do the opposite in order to get the inner limit of the outer solution. So we go to the outer solution, we now replace x by epsilon x tilde, right? And then we take the limit epsilon going to 0. So why do we make this substitution? Well, this substitution indicates what quantity is going to be order 1. So if you are in the inner solution and we want to take its limit far from the wall, then x tilde goes to infinity, but x is order 1. So by substituting x tilde by x by epsilon, we can say x is order 1 and then epsilon can be taken to 0 and the limit was well defined. On the other hand, in the outer limit, when we want to come near the wall, it's x that takes vanishingly small values because we're trying to approach x equal to 0. So instead of doing that, we replace x by epsilon x tilde. X tilde must have order 1 values here because we're approaching the wall, and epsilon can be taken to 0 to take our limit. So let's do that in our solution now. Right, so from the inner solution, if I replace, let's just do it and so in a systematic way. So it's the limit of epsilon going to 0 of the following, where I replace x tilde by x by epsilon. So I'm looking at terms up to order epsilon. Right, so this comes from the inner solution, and this must be equal to again the limit of epsilon going to 0. In the outer solution, we substitute x as epsilon x tilde, Alright, and so now we can apply the limits, recognizing that we should retain terms to order epsilon because we are looking at the problem up to order epsilon. So what we get is the following: b0 into 1. Now what survives here? If we take epsilon going to 0, this is equivalent to 1 upon epsilon x by, 1 upon e to the power x by epsilon. As epsilon goes to 0, that goes to infinity. And this basically becomes 0. and there is no first order term because such a term has exponentially small contributions, and you can't really write a Taylor series expansion for such a term. In other words, as epsilon goes to 0, this term is going to be smaller than any integer power of epsilon. So what I get from here is simply b naught into 1 plus these epsilons cancel, so I get minus x, right, plus b1 now, and the same exercise will apply here, but I'll be multiplying it with an epsilon, right, and this term is exponentially small and falls out. So this must be equal to, now on the other side, we can do a Taylor series expansion here, unlike in this case. So for small epsilon, I will get 1 minus epsilon x tilde, right, plus a naught plus epsilon. Again, I will have 1, right, minus epsilon x tilde I can drop because there's already an epsilon multiplying this term, so it will become epsilon square if I try to retain the first order Taylor series expansion of e to the minus epsilon x tilde. So I just retain the 0th order term, so it's epsilon into 1 plus epsilon into a1. Alright, that looks good. And so now we can, by matching these two at their orders, we can determine the values of b naught and b1. First of all, we recognize that basically this minus x is same as minus epsilon x tilde, right? So these terms cancel off, and what we are left will allow us to determine the fact that b naught is simply 1 plus a naught, and similarly b1 is also 1 plus a1. Quite nice. So if we eventually determine a naught and a1, in this case, because we're working with the boundary layer near 1, it must be that a naught and a1 are determined from the boundary layer at x equal to 1. Then these are known values, and we can from there determine the corresponding constants for the boundary layer solution at x equal to 0. So that completes our problem, and we saw how the matching procedure worked very nicely to allow us to determine these two constants. Okay, so from here we have a solution right now in terms of a naught and a1. So let me write that down. And so we have f inner equals so let me now write x tilde as x by epsilon, just to write everything in one variable. So this actually is a 0th order term, you can see, if we multiply throughout by x. Sorry, minus 1 plus a1 times 1 minus e to the minus x by epsilon. Okay, that looks good. So we now have our boundary layer solution entirely determined and well matched with the outer solution. Alright, but it remains to see what happens at the boundary layer, or to see whether there is a boundary layer at x equal to 1. So the fact that the analysis worked properly for x equal to 0 implies that this is in fact the boundary where there is a boundary layer. But let us see what happens if we had started our analysis by looking for a boundary layer at x equal to 1. And let us see how the analysis would tell us that there is in fact no boundary layer there. So basically, what if we search for a boundary layer near x equals 1? Right, that's what we will explore now. So essentially we have to go back to our problem and again look for a stretching of the coordinate. and we would, I mean, because our analysis is the same, nothing really changes if we go for one boundary to the other. We would still reach the same conclusion that alpha should be -1, except now the transformation, instead of just being x tilde is equal to x epsilon to the alpha, I would have it equal to 1 minus x epsilon to the alpha, because I want to be near the boundary of x equal to 1. So let's make that transformation now. And we would know that alpha is equal to -1 if we look at the balance of the terms as we did before. And so is just 1 minus x by alpha, such that as x approaches 1, x bar is going to 0. Whereas if I am within the domain, basically if x becomes much less than 1, then x bar would go off to infinity for small values of alpha. And that's basically how we would like, that's what we would like to construct for a boundary layer coordinate, stretched boundary layer coordinate at x equal to 1. And the boundary condition here now is that if x bar is equal to 0, we have the solution must be equal to 1. Oh, sorry, this is a silly mistake. This alpha should be epsilon, of course. Yes. Okay. So now we can look at the equation near this boundary. It would be the same as what we had obtained before, except for the right hand side. Now x bar square there is a minus sign, of course, because there is now a negative sign here, right? Because x bar is, d by dx bar is minus d by dx, so it gets a minus sign here, whereas there are two derivatives here, so it remains positive in this case. And this was minus e to the minus x, which is now minus 1 minus epsilon x bar, right? This basically means x is equal to 1 minus epsilon x bar. X bar goes the other side. Okay, that looks good, but this is equivalent to e to the minus 1 into e to the plus epsilon x, which is e to the minus 1, and if I Taylor expand this, it's 1 plus epsilon x plus order of epsilon square terms. Alright, so I'm now in a position to look for my expansion. So let's now expand the solution in let's say H, because this is now we are searching for yet another perturbation solution. And if I make the substitution here, multiplying throughout by epsilon, of course, as I had said, there are actually no partial derivatives, they are all total derivatives, must be equal to 0. So this form of the solution is exactly what we had for the other boundary, except that where there was a plus sign here in front of the first derivative, there's now a minus sign. So what this will do is it will change the sign of the exponential and all else will be the same. So my solution would now go as is equal to some constant, let's call it d naught now, e to the plus x bar, right? Because the minus sign had come from this, earlier this was a plus sign in the boundary layer x equal to 0. Here it's a minus sign. So instead of e to the minus x tilde, I'm getting e to the plus x bar. And then I'll have another constant of integration sitting here. I now know that h naught of x bar equal to 0 is actually equal to 1 to satisfy the corresponding boundary condition. So this means 1 equals d naught plus e naught. So e naught is 1 minus d naught. And so h naught is equal to 1 plus d naught into e to the x bar minus 1. This makes sense. Yes, that looks right. So then similarly we can look at the next order. It would be the same but with minus e to the minus 1 as a forcing term, right? We would have epsilon e to the minus 1 sitting out here. Sorry, not epsilon, you just have e to the minus 1, the epsilon coming from the denominator of the other side. So you would have a constant forcing term at first order, but otherwise the problem is the same, and you can show, which I will leave it up to you to work out, that h1 simply becomes e to the minus 1 times x bar plus d1 times e to the x bar minus 1. So it's basically the same as we had at 0th order, except for the change of sign in front of the x bar and in front of the exponential terms. Okay, so this is now the so-called inner solution at the boundary x equal to 1. And we need to find the constant d1, which we can obtain only from matching with the code. But already you can see, just give me a sec while I try to get one node to comply. Yeah, that looks okay. Get myself some more real estate here. All right, so we now have what is now the f inner near x equal to 1, of course. Right, and then again we have to match this with f outer, which from my experience of course was e to the minus x plus a1 sorry, this is a naught. Yes, that looks right. Okay, so now we again try to do Van Dijk's matching. Right, so remember this is equivalent, we need to take the limit of epsilon going to 0 of the inner solution after substituting x bar as 1 minus x by epsilon. Right, so we will get d naught. Sorry, first let's write down the 1 plus d naught into e to the 1 minus x by epsilon minus 1 plus epsilon times e to the minus 1 x bar plus d1 times e to the 1 minus x by epsilon minus 1. And all of this must equal what happens if I take the limit epsilon going to 0 in the outer solution, but after substituting x as x in terms of x bar, which here is 1 minus epsilon x bar. Alright, so let's see what that gives us. So the first term as epsilon goes to 0 is just 1. And now the second term is very interesting. We see that we have an exponential term here, 1 minus x upon epsilon. But this time we know as epsilon goes to 0, this term is not going to become small and go to 0 as it did in the boundary near x equal to 0. Rather, because 1 minus x is always a positive quantity, taking epsilon to 0 basically blows off this term to infinity. So I get an arbitrarily large term as I take epsilon going to 0, and such a term cannot be balanced by anything in the outer solution, right? Because as epsilon goes to 0 here, I get only finite quantities at first and second order, whereas here I'm getting a quantity that goes to infinity. So the only way I can match this solution with the core is if I set d naught to be equal to 0. So already the matching has told me that d naught must be 0. Similarly, you will see that d1 also must go to 0 because of the same argument here. Right, you could have anticipated this at the time of obtaining the solution even in x bar. So you will see that as x bar, if x bar is close to 0, which means x is close to 1, this solution behaves fine. This term behaves fine, but if x bar starts increasing, the solution increases exponentially, and therefore it cannot be expected to match the solution near the core, which corresponds to very large values of x bar when you take the limit of small epsilon. So now this is what tells us that there is no boundary layer near x equal to 1, because in contrast to the case of the boundary near x equal to 0, the boundary layer solution that we obtain is not feasible in this case where x is equal to 1, because the boundary layer solution actually blows up as we move away from the boundary. So what that really means is that the only true solution is if the boundary layer terms are, basically there is no boundary layer structure because both d naught and d1 are set to 0. All that survives are these constant terms, which is actually, you see, what we would obtain if we had simply taken the solution in the core and applied the boundary condition at x equal to 1 directly. But now, since we're anyway in the process of matching, let's see how we can determine a0 and a1, how their values will come out from the matching procedure naturally. Yes, so now recognizing that d0 and d1 must both be 0, this limit of the outer limit of the inner solution simply gives us the following. Yes, that's all. And this must be equal to, so as epsilon goes to 0, right, I will have a e to the minus 1 times 1 minus epsilon x bar plus epsilon times a1 plus e to the minus 1 into 1 so I just want, because I don't want, if I take the other epsilon term, it becomes epsilon squared, right? So it's just plus e to the minus 1. Okay, now if I match terms, well, we should recognize that this term minus epsilon e to the minus 1 x bar and this term over here can be related to this term, right? Let's just see how it works out. So we should, to match it, let's write it in terms of one variable. Oh, sorry, I had forgotten to replace it here. So yes, this is not x bar, this is 1 minus x by epsilon. So similarly, this is 1 minus x by epsilon. So this and this will cancel out. And I also forgot the a0 from here, so there is a plus a0 here. Okay, so now by matching, we basically have 1 here. Well, Right, so let's just expand this out first. This would have been, right, so what is this term? This term is basically e to the minus 1 minus epsilon e to the minus 1 into epsilon x bar. But epsilon x bar is simply 1 minus x. 1 minus x. Right, so this term would cancel off with that term there. So all I get at leading order is 1 is equal to e to the minus 1 from here. This term cancels off with that term. Plus a naught. So therefore, a naught is given as 1 minus e to the minus 1. And similarly, at the next order, at order epsilon, right, we basically have 0 on this side must be equal to a1 plus e to the minus 1. So therefore, a1 is minus e to the minus 1. And thereby we determine both our constants a naught and a1. And now you can go back and check that if we had somehow guessed that there is no boundary layer in x equal to 1, and we had simply taken the outer solution and substituted the boundary conditions f equal to 1 at x equal to 1, this is exactly the values for a naught and a1 we would obtain. But even if we didn't know that and we assume that there is a boundary layer, proceed with the analysis itself will tell us that the terms multiplying the boundary layer structure have to go to 0 because that boundary layer structure is blowing off to infinity away from the boundary. And the terms that survive are just sufficient to allow us to determine the unknown constants in the outer solution. So it basically it reduces to becoming equivalent to simply substituting boundary conditions at that boundary to determine constants in the outer solution. But now at the other boundary, the boundary analysis will proceed smoothly, give us a new unknown constant that needs to be determined to find a valid boundary layer structure, and that will be obtained by using Van Dijk matching. So you see that the procedure works out quite smoothly, even if you don't know where exactly to locate the boundary layer, because you can simply assume there is a boundary layer and the analysis itself will guide you systematically.